Here's something I want you to think about right now. Cast your mind back. You're 11 or 12 years old. You sprint across a field all morning, crash your bike, scrape your knee, dust yourself off, and you're back running again within minutes. No warm-up needed, no recovery protocol, no 2-day soreness. You were basically unstoppable. Now, flash forward. You're 40, 50, maybe 60. You haul yourself up 3 flights of stairs, and you have to pause at the top to catch your breath. You sit through a long meeting, and by 2 in the afternoon, your brain feels like wet cement. You sleep 8 hours and still wake up tired. What happened? Now, you might say, and most people do, well, that's just aging. And I understand the impulse, but think about what you've actually said. You've given the thing a name. You haven't explained anything. A biologist might be satisfied with naming it. A doctor might prescribe something for it. But a physicist is not satisfied with labels. A physicist wants to know the mechanism, the actual chain of cause and effect, written in the language of atoms and molecules and energy that transforms a tireless 12-year-old into someone who needs an afternoon nap. And here's the thing. When you actually chase that mechanism down, when you follow it all the way to its roots, you don't end up in a biology textbook. You end up in thermodynamics. You end up staring at the same laws that govern steam engines and collapsing stars and the ultimate fate of the universe. And those laws have something very specific and very personal to say about your body. So here's what we're going to do. By the time we're done, you're going to understand what energy actually means inside a living organism. You're going to understand entropy, not as a vague buzzword, but as a real physical quantity that is actively working on you right now. And you're going to understand why aging, viewed through the lens of physics, isn't a malfunction. It isn't bad luck. It is the inevitable, mathematically required consequence of being alive. First things first. When I say energy, I mean something precise, not a vibe, not a feeling, not the kind of thing that gets sold in supplements. In physics, energy is the capacity to do work, full stop. It's measured in joules or calories. It follows strict mathematical laws. It can be converted from one form to another, but it cannot be created from nothing, and it cannot simply disappear. When you say you feel energetic, that corresponds to real, measurable chemical processes running at a certain rate inside your cells. When you feel exhausted, the chemistry is genuinely different. You can detect it in your blood, in your tissues, at the level of individual proteins. Fatigue is not weakness. Fatigue is physics made personal. Now, let's start with something concrete. Lunch, say. A bowl of rice, some chicken, maybe a piece of fruit. What does your body actually do with that? Most people have a rough answer. It gives me energy. True, but imprecise. Let's get specific. The carbohydrates in that rice get broken down through digestion into glucose, a simple 6-carbon sugar molecule. That glucose travels through your bloodstream and gets absorbed into your cells. And inside each of your cells, tucked away in the cytoplasm, are these extraordinary little structures called mitochondria. Mitochondria are fascinating objects. They're about the same size as bacteria, and that's not a coincidence. The current scientific consensus is that roughly 2 billion years ago, a primitive cell swallowed a bacterium and instead of digesting it, kept it. The bacterium turned out to be extraordinarily useful at extracting energy from molecules, and the relationship became permanent. You are, in a very literal sense, a consortium of ancient organisms. Your mitochondria carry their own DNA to this day, a relic of their independent bacterial past. These mitochondria take that glucose and run it through a cascade of chemical reactions called cellular respiration. But they don't burn the glucose the way you'd burn wood in a fire. That would be wasteful, uncontrolled, and lethal. Instead, they capture the energy in a controlled, stepwise way and lock it into a molecule called ATP, adenosine triphosphate. ATP is a remarkable piece of molecular machinery. Picture a spring that's been compressed. ATP has 3 phosphate groups chained together, and the bond holding the last one in place is under high chemical tension. When your cell needs to do something, contract a muscle fiber, transmit a nerve signal, build a new protein, it breaks that bond. The spring releases, energy comes out. The used ATP, now called ADP, gets shuttled back to the mitochondria to be recharged and sent out again. Here's where the scale becomes genuinely astonishing. Your body contains at any given moment roughly 50 grams of ATP. That's it, a small handful. Yet, in the course of a single day, your body synthesizes and consumes somewhere around 40 to 50 kilograms of it, more than your own body weight, all in a molecule you only have 50 grams of at once. Each molecule is recycled hundreds of times per day. In a single second, one cell, and you have 37 trillion of them, goes through approximately 10 million ATP molecules. 10 million per second, per cell. This is happening right now, silently, without your awareness, at a scale that makes the most advanced human engineering look primitive. Your heart beating? ATP. Your eyes reading these words? ATP. The warmth you feel in your hands right now, that's waste heat from ATP production. Every single thing your body does is downstream of this one molecule being manufactured in your mitochondria. So now the real question: why does that factory start underperforming? The answer lives inside the mitochondria themselves. When mitochondria extract energy from glucose, the process isn't clean. It's like any combustion process. There's exhaust. In this case, the exhaust takes the form of molecules called reactive oxygen species, or free radicals. You've probably heard of them. They're chemically aggressive. They have an unpaired electron, and they'll react with almost anything in search of a partner: proteins, cell membranes, and most crucially, DNA. Here's the cruel geometry of the situation. Mitochondria have their own DNA, separate from the DNA in your cell's nucleus, and that mitochondrial DNA sits right next to the machinery producing the free radicals. It's like storing your paper archive directly beside an open furnace. On top of that, mitochondrial DNA lacks the protective protein packaging that nuclear DNA has, and the repair enzymes available to fix mitochondrial DNA damage are far less sophisticated than those guarding nuclear DNA. So every day, every hour, the mitochondria generate the chemical equivalent of sparks, and those sparks land on the most vulnerable parts of the structure. Over years and decades, the damage compounds. Mitochondria that have accumulated errors become less efficient. They extract less ATP per molecule of glucose, and they produce more reactive oxygen species doing it. More damage leads to more inefficiency, leads to more damage. It's a feedback loop running in the wrong direction. And you feel it as the gradual retreat of your stamina, your recovery speed, your capacity to handle physical and mental demands. Now I want to step back from the biology and show you where all of this comes from, because there's a deeper layer, and it's one of the most profound ideas in the history of science. In 1944, the quantum physicist Erwin Schrödinger, yes, the cat guy, wrote a short book called What is Life? He was trying to answer a question that physicists had largely ignored. What makes a living organism different from a rock? Both are made of atoms, both obey the same physical laws, so what's special? Schrödinger's answer was beautiful and strange. He said living organisms survive by consuming what he called negative entropy from their environment. To understand that, you need to understand entropy itself. Entropy is a concept that comes from thermodynamics, formalized in the 19th century by a physicist named Rudolf Clausius. It's often described as disorder, but I prefer to think of it as the dispersal of energy. When energy is concentrated and organized, entropy is low. When energy is spread out and degraded, entropy is high. Here's a picture. You have a hot cup of tea sitting on your desk. The tea is full of organized thermal energy, molecules vibrating rapidly, concentrated in one spot. The air in the room is cooler, calmer, more uniform. Leave the tea alone for an hour. What happens? The heat flows from the tea into the room. Eventually, everything is the same temperature. The energy that was concentrated has spread out. Entropy has increased. Now, here's the critical point. You never see the reverse happen. You never see a cold cup of tea spontaneously get hotter while the room gets cooler. That would be a decrease in entropy, and it doesn't happen. This is the second law of thermodynamics. In any closed system, entropy can only increase or stay the same. It never spontaneously decreases. Order gives way to disorder. Concentrated energy spreads out. Hot things cool down. Organized things decay. What makes this law uniquely profound is that it's the only fundamental law of physics that distinguishes the past from the future. Newton's equations work equally well forwards and backwards in time. Maxwell's equations, quantum mechanics, all of them are time symmetric, but the second law is not. It gives time its arrow. Entropy was lower in the past and will be higher in the future. That's not a coincidence. It's the physical basis of everything we mean when we say before and after. So, back to Schrödinger. If entropy must always increase, how does a living organism maintain its extraordinary internal order? How does your body, with its precisely arranged proteins and membranes and neural circuits, hold itself together year after year when everything around it is falling apart? The answer is that your body is not a closed system. It's an open system. It imports highly organized, low-entropy energy from outside in the form of food, and it exports high-entropy waste heat and chemical byproducts. It maintains local order by accelerating disorder elsewhere. The total entropy of the universe still goes up as required, but inside your body, temporarily, order is preserved. Life is essentially a process of swimming upstream against the current of entropy. You keep yourself organized by constantly consuming order from your environment and dumping disorder into the world around you. Now, watch what happens to this picture as you age. Every step in that energy conversion chain, food to glucose, glucose to ATP, ATP to mechanical work, loses something to inefficiency. No conversion is perfect. The second law guarantees this. Real engines always produce waste heat. In a young body, the machinery is in excellent shape. The mitochondria capture around 40% of the chemical energy in glucose as usable ATP. That sounds low, but it's actually remarkable, better than most car engines. The remaining 60% becomes body heat. But as mitochondria accumulate damage over decades, that efficiency drops, maybe from 40% to 35%, then 30%. The absolute numbers seem modest, but across trillions of cells, running billions of reactions every second, the cumulative effect is enormous. More of your food goes to heat, less becomes actual work. And equally important, the damaged mitochondria lose their ability to rapidly scale up production when demand increases, like during exercise, stress, or cognitive effort. The baseline still functions, but the peak capacity shrinks. Here's something that researchers discovered relatively recently, and it surprised almost everyone. A large international study tracked the metabolic rates of over 6,000 people across a broad range of ages using a precise measurement technique called doubly labeled water. The expectation was that metabolism would slow progressively from your 20s onward, that famous "my metabolism isn't what it used to be" complaint. What they actually found was different. Adjusted for body size and composition, metabolic rate is essentially flat from age 20 to around 60. Your cells aren't burning less efficiently in your 30s or 40s. The total energy use does tend to drop during that period, but that's almost entirely explained by changes in body composition. People lose muscle mass and gain fat. Muscle is metabolically expensive, fat is cheap. As the ratio shifts, so does total energy demand, but the cells themselves aren't slowing down. This matters. It means that for most of your adult life, your perceived energy decline is substantially within your control. Maintain your muscle mass, stay active, and your cellular energy output doesn't have to fall. After 60, though, something genuine changes. From 60 onward, there's a real decline in metabolic rate, roughly 0.5% per year, that persists even after accounting for body composition. By the time you're in your late 80s, your cells are burning meaningfully less efficiently than they did in middle age. This is the accumulated mitochondrial damage showing up in the data, not lifestyle, not muscle loss, the machinery itself. Let me give you a way to visualize what's happening at the cellular level using a concept from thermodynamics called free energy. Not all energy is equally useful. The total amount of energy in a system is conserved, that's the first law. But some of that energy is available to do work, and some of it is locked away in a form that can't be extracted under the current conditions. The energy that can actually drive reactions and do work is called free energy. Think of it this way. Imagine a dam holding back a reservoir of water. The water behind the dam has potential energy. It can fall, turn turbines, generate electricity. That's the food you eat. Your mitochondria are the turbines. When they're new and precisely engineered, they capture most of that falling water as useful electricity. When they're corroded and worn, water leaks around the turbines, through cracks, producing noise and heat, but not power. The water still falls, the energy is still there, but less and less of it does anything useful. That's cellular aging at the thermodynamic level. It's not that you run short of fuel, it's that your conversion machinery becomes progressively less capable of turning fuel into work. Now I want to tell you about something that makes this even more interesting. Your cells have a quality control system for their mitochondria, and it's extraordinary. The process is called mitophagy, mitochondria plus the Greek word for eating. When a mitochondrion accumulates enough damage to become more liability than asset, the cell marks it for destruction. Membrane structures wrap around it, a molecular disposal crew breaks it down, and the salvageable parts get recycled for new construction. It's ruthlessly efficient housekeeping. There's also a molecular switch called AMPK, AMP-activated protein kinase. Think of it as the cell's fuel gauge. When ATP levels drop, AMPK activates, and it triggers a cascade of repair and renewal processes, including mitophagy. It also stimulates the production of new mitochondria, a process called mitochondrial biogenesis. Your cell literally builds new power plants when it detects that the old ones are underperforming. Here's what's remarkable about this. The things that activate AMPK most powerfully are exercise and moderate fasting. When you work out hard, ATP temporarily drops in your muscle cells. AMPK fires. Mitophagy clears out the damaged mitochondria, and new ones are built to replace them. You've stressed the system, and it's responded by upgrading itself. This is why regular exercise doesn't deplete your energy long term. It improves the efficiency of energy production. You come out the other side with a higher quality fleet of mitochondria. In a young person, this system runs like clockwork. Damaged mitochondria are swiftly identified and removed. Fresh ones are built. The ratio of functional to dysfunctional power plants stays high. In an older person, mitophagy becomes less efficient. The quality control falters. Damaged mitochondria linger longer, accumulate, and drag down the performance of the whole cellular neighborhood. But let's go one level deeper, because there's something even more fundamental driving all of this. Something that connects your biology to a principle that governs information itself. Your cells are constantly rebuilding themselves. Most of the protein molecules in your body right now didn't exist 6 months ago. Your bone mineral turns over on a timescale of years. Even your DNA is constantly being damaged and repaired. You're not the same physical substance you were a decade ago. So why don't you just keep rebuilding yourself to the original specification? Why does the structure gradually degrade even though you're constantly replacing the parts? The answer is that every act of copying introduces the possibility of error. Your cells read their DNA and build proteins from those instructions. The copying machinery is astonishingly precise. It makes roughly one mistake for every billion letters of DNA copied. But 1 in a billion isn't 0, and you have trillions of cells, each with 3 billion letters of DNA. Errors accumulate. Worse, the repair machinery that catches and corrects those errors is itself made of proteins. Proteins built by reading the very DNA that's accumulating errors. As the instructions degrade, so does the quality of the repair crew. As the repair crew degrades, more errors slip through. It's a deteriorating feedback loop operating at the level of molecular information. There's a physicist named Rolf Landauer who demonstrated in the 1960s that information processing and thermodynamics aren't separate domains. They're deeply connected. Erasing or losing information has a physical cost. It produces heat. Information is not abstract. It is physical. It obeys thermodynamic laws. Your genome is a physical information store. And just like any physical information store operating in a noisy environment, and the interior of a cell, with its free radicals and thermal fluctuations, is an extraordinarily noisy environment, errors accumulate over time. The second law applies not just to the chemistry of your metabolism, but to the fidelity of the molecular instructions that govern it. Now let me tell you something that some physicists find striking. When you add up all the entropy that a human body produces over a complete lifetime, the total thermodynamic irreversibility of a human life, measured in joules per Kelvin, the number comes out roughly similar across different individuals. Some researchers have called this lifespan entropy production, and it suggests something almost poetic, that a human lifetime represents a fixed thermodynamic budget. You're born with the capacity to process a certain quantity of order before the accumulated wear and tear becomes insurmountable. This idea connects to something called the rate of living theory. The core observation is this: across the animal kingdom, animals with faster metabolisms tend to have shorter lives. A shrew, whose heart beats over 1,000 times per minute, lives perhaps 2 years. A bowhead whale, metabolizing at a slow and stately pace, can live over 200 years. A hummingbird and an elephant burn through roughly the same amount of energy per gram of body tissue over their respective lifetimes. They just do it at vastly different speeds. The rate of living theory in its original form is too simple. It doesn't fully account for birds, which have high metabolic rates but surprisingly long lives, apparently due to unusually efficient antioxidant defenses and mitochondria that leak fewer free radicals. But the core thermodynamic insight survives. The faster you process energy, the faster you accumulate damage, and the faster you approach entropy's finish line. So where does this leave you practically? The second law doesn't specify how fast entropy has to increase. It just says it must. And that means the rate is something you can influence, even if you can't reverse the direction. Exercise, particularly resistance training, is the single most powerful intervention we know of for slowing mitochondrial decline. It activates AMPK, stimulates mitophagy, drives the production of new mitochondria, and keeps the ratio of functional to damaged power plants favorable. The short-term energy cost pays for itself in long-term efficiency gains. Sleep matters more than most people appreciate. During sleep, your body runs repair processes that it doesn't prioritize during waking hours. Growth hormone peaks, cellular cleanup accelerates, brain cells that have accumulated waste products from a day of neural activity flush them out. Chronic sleep deprivation is essentially running your power plants at full speed while skipping scheduled maintenance. Moderate caloric restriction, eating somewhat less than maximum appetite, has been shown across many organisms to extend healthy lifespan and preserve mitochondrial function. The mechanism involves AMPK, mitophagy, and reduced oxidative stress. You're producing less exhaust per hour. Stress management matters too, because chronic psychological stress elevates cortisol, which at sustained levels is genuinely corrosive to cellular function. The vicious cycle of stress, poor sleep, inflammation, and mitochondrial damage is well documented in the research. None of this will let you escape the second law, but understanding the mechanism tells you exactly where the leverage points are. Let me close with something that I find genuinely moving. The atoms currently assembled into the pattern we call you have been around for billions of years. The hydrogen in your body was forged in the first minutes after the Big Bang. The carbon, oxygen, and nitrogen were manufactured in the nuclear furnaces of stars that exploded long before our solar system existed. You are not just metaphorically made of stardust. You are, in the most literal chemical sense, a temporary arrangement of ancient stellar material. Those atoms have been part of countless other arrangements before this one: rocks, oceans, plants, animals, other people. They will be part of countless other arrangements after this one. What makes you remarkable isn't the atoms, it's the pattern they've been organized into. The pattern that processes energy, maintains its own structure, repairs itself, thinks, and asks questions about the nature of reality. So when you feel tired, you're not experiencing a personal failure. You're experiencing the second law, real, measurable physics acting on real, measurable chemistry in your cells. There is no shame in it. Water flows downhill not because it's weak, but because that's what physics requires of it. And when you exercise, sleep well, eat thoughtfully, you're not magically overcoming physics. You're working with physics. You're optimizing the thermodynamic processes inside your body. You're clearing out damaged mitochondria, building new ones, giving your repair systems time to catch up. You're swimming upstream more efficiently, even though the river always runs the same direction. Here's what I think is the most remarkable thing of all about this situation. A candle burns. It consumes fuel and produces light and heat. But the candle doesn't know it's burning. The flame doesn't understand combustion. You do. You are, as far as we know, the only arrangement of matter in the known universe that can look at itself and understand, at the level of atoms, molecules, thermodynamic laws, and quantum physics, exactly what it's doing and why. You can watch your own entropy increasing and comprehend what it means. So here's my question for you. Now that you know the mechanism, not just the label, but the actual physics underneath the fatigue and the aging and the finite span of a human life, does it change anything for you? Does understanding the flame make the burning feel different? Think about that.